I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
Metrology and inspiration for science, the new system of units. So I'm from the National Laboratory for Metrology Research in Turin, the north of Italy, and professor of physics at the University of Florence, and also associated to the Lens Laboratory in Florence. My name is Diederik Wiersma. So the science of measuring things is of course very important in many fields of science. So physics and chemistry and biology. Progress in science is relying on measurements and good measurements, accurate measurements and reliable measurements. But on top of that, the science of measurement is all around us. When we go in daily life to measure small things very accurately, things like distances, but more complicated if we go into production side of some industry, then we will have sensor data, we will have complicated things to look at and to make sure that this data is reliable. This is an example of a production plant which is all using robots and sensors. And then over there we have the stock market in Italy. Now you would wonder, why do you need to measure things at the stock market? Well, the stock market needs a good time signal. So that's another example of measuring things, measuring time very accurately and make sure that everybody agrees on what time it is. This timestamp is very important because trading in the stock market is sometimes done very rapidly, even by computers. And that means that everybody has to agree on exactly when something was sold and something was bought. And this is the control room, let's say, where we generate this time signal and send it out for the use in Italy. So this is our control room where the time signal is generated for Italy. And this has to be then coordinated with the time signals in other countries. Now then, measuring time not only is useful for the stock market, but to measure a position using a global positioning system, like depicted over here, you also need time. You need accurate time, and everybody has to use the same time signal. This is an example of a satellite system called Galileo, which is the first European navigation system. And the time signal for this navigation system is again coming from our laboratories in Turin. But then there are many other areas where you want to make sure you get the right information and you get the right measurements. Something like building a house. You need to have accurate measurements or reasonably accurate measurements of where things are going to be. You want to make sure that when you buy electricity, that the electricity meter in your house gives you the right number, the fair number, so that you're buying exactly what you're paying for. Then there is trade on a big scale, but also trade on a small scale. If I'm here at the market, I want to make sure that what I'm buying is actually what I'm paying for. Now, to make sure that what we're measuring is done with units that we all agree upon, we have this beautiful international system of units, the SI, the meter, the second, the kilogram, but then you have the ampere, the Kelvin, the mole, the candela. These are the 7 primary units of measures, and then you a measurement, and then you have the secondary ones which are derived from that. All these countries agree on that, and that's an important matter, because that means that they all use the same definition of the meter, the kilogram, the second. That seems trivial at the moment today, but in practice this was quite an effort to get to this. And there has been recently a very interesting event in this context, and that's why I'm talking to you also today about this. And that is that there has been a conference recently in which all these countries came together and agreed upon a redefinition of this system. And in particular, the kilogram has seen an important improvement in its definition. What is interesting also is that these countries, they come together. Here you see representatives from all these governments that are together in this big hall that are taking a decision. And all these countries, they vote on this and they have to agree. So there has to be a unanimous vote of many countries that come together, that might have political friction, that might have even been in war or still are. But through science, when they have to take a scientific decision, they manage to collaborate, they manage to come to solutions, and they manage in the end to vote unanimously for a new system. And I think that's quite a beautiful thing, because that means that science, and maybe also art and other areas, but science in this case can help to have countries come closer together and maybe overcome tensions and difficulties. So science as such is also a step in the right direction to have a more peaceful world, I think. This was the resolution that had to be voted on, and I will explain that in a second. This was a photo that I took at the moment when the voting started. And now, where was this vote about? This was about a new system in which you have these 7 units of measurement, so the meter, the second, etc. And now in this new system, these units are based on the natural constants. And these are the spheres around this. You have the Planck constant, the Avogadro constant, then you have the Boltzmann constant, etc., and so on and so forth. And these natural constants, they form the basis of this new system. And why this is a good idea, I want to talk to you about today. So how to define a system of units by defining the values of some of the natural constants. That is what this is about. So to explain this, let me start with a short story of length. In the beginning, when human beings started to wonder how to measure something, for instance, how to measure length, they started by using the human body as a reference. So a hand, an inch is actually coming from your thumb, foot, cubit, that's your forearm, phantom, that's from fingertip to fingertip, yard is from nose to fingertip. Now this is very convenient because you always have a human body somewhere at hand when you're measuring something, your own body, for instance. But it's not very consistent. If I buy something from somebody on the market, which is as big as this guy, and he is going to measure it in arm length, I will get much more material from him than if she is selling in the same unit of arm length and using her own arms to measure that with. So the Egyptians then had a good solution, actually, a reasonably good solution. The Egyptians were obsessed, they were fanatic about measuring things accurately. They were very good at that also. They thought this was very important. And what they did, they took the body of not just anybody, they took one very important body, namely the body of the pharaoh. This was the cubit, this was the palm. Now, taking one specific body, namely that of the pharaoh, meant that everything was referring to the same units, which is such a good idea. But then if you go to the marketplace and you want to buy something or you want to build a pyramid, you cannot ask the pharaoh all the time and disturb the pharaoh all the time to use his body as a reference for your measurements. You cannot do that. So you have to make a copy. Of the cubit, they would make a primary copy in granite, and out of this primary copy then they would make secondary copies, secondary cubits in wood. And these secondary cubits that then the people would use to measure things with, they had to be calibrated each month. And actually the system was very efficient also because there was the death penalty for non-compliance, and that helped a lot in getting the system accurate. Now look how surprisingly modern this system was. They measured, they built these pyramids with a baseline consistency of 0.025%, which is amazing if one realizes which period of our history we're talking about and what the instruments were that were available. And within the same context, the pyramids are square to about 12 arc seconds, which is also an amazing effort. So this is an example of such a cubit. This is a photograph that I took when I visited the beautiful Egyptian museum in Turin one day. So this situation lasted actually after the period of the Egyptians. This lasted for quite a long time, and similar artifacts were used throughout Europe, varying from town to town. So we all the time have artifacts, physical objects, as a reference for measuring length. This of course is not very handy if you consider that a foot in Rome over here would be something like less than 30 centimeters, while a foot in Torino would be something like more than 50 centimeters. That is not a very consistent system. And it's not very easy to compare measurements that are taken in different places, of course, in this way. This is an example of a table which was then used to convert all those units. You have the atomo, the punto, that's the Italian, here atomo oncia. You have all sorts of units, braccio lungo, braccio corto, which means the long arm length, which was used for textile in general, the short arm lengths, which were used for silk. And then the issue was also that you had to specify where the measurement was taken. So it was the one which was in Novara, for instance, or the one in Milan, or the one in Turin, or that was kind of chaotic, this situation. Then the French came, the French Revolution in particular, and they wanted to have a system which would be for all the peoples and for all times. So the revolutionary dream was to revise this system in something that would be universal. And the idea then became to use the earth as a reference. The earth is democratic, if you want, it's everybody's. And the distance now from the North Pole to the equator was taken as the reference for the meter. Just to make sure that everything was universal, the meridian had to pass through Paris. Well, you can give them this credit because it was the French who came up with the idea. Anyway, the meter was then defined as 1/10,000,000th of the distance of the equator to the North Pole, which translates into a distance of 10,000 kilometers. This was as such stable and more universal than using a forearm or using a body part, things like that. But not that easy to measure. Now I have the Earth as reference, and that means that if I want to use that, I need to know how big it is. So I need to measure this distance actually, at least once. And that was quite an effort. The technology for measuring distances at that time was that of triangulation, invented by Snellius from the Netherlands, probably amongst others. And this works as follows. You look at some tower, some top of a mountain, or some other point which you can identify clearly. You take two of them and you measure the angle in between them. Then you go to one of them and you look at other points and you measure again the angle. And by measuring many of these angles, you can construct triangles, hence the terminology triangulation. You can construct triangles, and that's actually quite an accurate way of measuring distances. Now, this was an effort here by these two people, Méchain and Delambre, to measure the distance from Barcelona to Dunkirk, which is in the north of France. This is a distance of about 1,000 kilometers, a little bit more than that. So that's quite a distance to measure in this way. And remember that in total they had to measure all the way from the North Pole to the equator. So this was also only a little piece of the puzzle to solve. This already took them 6 years to do, and it was not easy because this was the French Revolution going on. So while they were doing this scientific project of doing these measurements, there was war going on. People were thrown in jail, people were killed, wounded, all sorts of dramatic things were happening around them, and they themselves were maybe thrown in jail from time to time or arrested or whatever. So there you go for a scientific project that is difficult because of the conditions around you. During the French Revolution, trying to measure the distance from Barcelona to Dunkirk. And so, like this, there have been many other projects, and in the end, the distance was measured, and that meant that the Earth was available now as a reference for measuring length. Here is an example of the meter, for instance. Here is an example of the meter in wood or in metal. Now, why again here now artifacts? Because the Earth as such is maybe universal, it is maybe accessible to everybody, but it is not handy at all as a reference if I want to measure something in practice. So again, artifacts or physical objects had to be made in order to use this definition of the meter in practice. And again, the world needed physical objects to do this. By the way, in the attempt to make everything decimal, which as such was very handy, the French Revolution, or the revolutionists, they also came up with the idea to make time decimal. Here you have time, which is now 10 hours in a day and 10 hours in the night, and 1 hour would be 100 minutes, and 1 minute would be 100 seconds. This is a photograph that I took in Paris in the Musée des Arts et Métiers, which as such is already a reason to go to Paris. It's a beautiful museum in which you can see all sorts of objects from the world of metrology, from the Industrial Revolution, and so on and so forth. And this watch is there displayed. It's a very rare object. I guess it has an immense value. Of course, we know that decimal time never actually had a big diffusion. Let's say people in the end didn't accept to convert also time into something which was decimal. This is the meter that at a certain stage during the meter convention in 1875 was defined. So this was now the prototype. This was now a bar made of platinum and iridium, metals chosen because they have the right properties. They are stable and many things like that. And scratches were made in this bar to define the meter. And then this was the definition of the meter, based on the measurements taken on the Earth, etc. But in the end, the world had to do again with a physical object as a reference for the definition of the meter. Now, this is not so easy because then at a certain stage I get into difficulty when I want to know this distance very accurately, because this is a scratch, that is a scratch. But at a certain stage, if I want to have these values very accurately, it becomes difficult to know exactly where I'm taking the scratch as a reference, and so on and so forth. So in practice, people didn't use that definition. In practice, they used a lamp, and they used a technology called interferometry. So they looked at interference fringes that were generated by an interferometer. And by looking at these interference fringes, they were capable of determining determining length in a much more accurate way than you could do by taking this bar with the scratches in it. So when technology went forward, this became the de facto definition. This became what people actually used to measure length. And that meant that meant that the world of metrology had to come up with a new definition. Technology went forward and a new definition had to come to take this into account. So the meter was redefined, not anymore as this physical object, but as a certain distance with reference to the wavelength in vacuum of the radiation corresponding to the transition of the levels to levels, atomic levels, of the krypton 86 atom. This is a krypton lamp from the NIST Museum in the United States. This lamp was a much more accurate way, and the technology allowed to make these measurements. So that's why the definition was made in this way. But the definition, in a way, was running behind the technological developments. Also because soon after this, the laser was invented. And the laser was a better way of measuring distances with interferometry than a lamp was. Here's an example of a photograph I made recently of a laser beam, just to give you a flavor of things. In this case, the laser is also diffracted here by a diffraction grating. And what is important is that the laser beam here, in this case of a helium neon laser, could be used in a much better way, could be used to get a much better measurement of length. So the definition again was running behind the technology which was available, and people were using lasers while the technology was, while the definition was still based on a lamp. So the obvious choice was to define the meter now in terms of a stabilized helium neon laser. But the risk was here to run behind facts, and then maybe a next technological development would again supersede the definition. No, the brilliant choice was now taken to redefine the meter in terms of the speed of light. That is, by defining the speed of light now as a fixed number. And by doing so, one would have access to wavelength through frequency over here, which has units of 1 divided by second, and this is here the speed of light. So the speed of light, meters per second. This is a frequency, for instance, a frequency of a transition in an atom. And here you have wavelength, which is in the unit of meters. Now, by doing it so, all future technological developments are embedded in the definition. So it's not necessary to update the definition anymore when future technological developments take place. So for the meter, the problem was solved. But for the kilogram, the situation was actually quite dramatic. And what we had so far for the kilogram was a situation which was actually quite primitive, because we had a physical object in a safe in Sèvres, close to Paris, at the BIPM, the Bureau International des Points et Mesures, which is kind of the international headquarters for the metrology community, and by the way, it's international territory. What was kept there in a safe is an object like we have over here. This was a metal cylinder. You see it here in a protected environment. A metal cylinder which was used as the reference for mass. So what you see here is what would be defined as 1. This would be my reference. This would be 1 kilogram. 1 kilogram by definition of the system. But to give you an idea of how absurd that is, to have a physical object, if I would touch this with my finger in the old definition, it would mean that the reference value would increase mass. And since this is defined as 1, that would mean that within that system of measurement, all other objects in the world would lose mass. So in a way, everybody would lose weight if I would touch this object, which is of course a kind of absurd situation which you cannot maintain. And this was, let's say, that is why we will put it in here in this beautiful protected environment, and we will keep it there for now. So that the kilogram was actually changing mass, you can see that in this graph over here, so that the physical object was actually not really constant. This is a comparison of the primary copy in the safe in Sèvres, which was from time to time compared with national copies, like the one over there. And this comparison didn't give always the same value. Actually, there were differences as big as 50 or 60 micrograms. And there was clearly a drift because over the years this situation was getting worse. So the new system now uses a natural constant to define the kilogram. And the choice was made to use the Planck constant for that. The Planck constant is kind of the energy of a photon at a certain frequency f. So if I have a photon which is at a frequency f and I multiply that frequency with the Planck constant, what I get is the energy of that photon. Now, I'm talking here about an energy, but you will say, well, really what you want is mass. And for that reason, we will use the knowledge that Einstein gave us that mass and energy are actually equivalent to each other, E is mc squared, where c squared is now known because we have fixed the speed of light for the definition of the meter. So c squared is a fixed value, and that means that we can use this equivalence between mass and energy directly. Say it in other words, the mass change of a particle when it emits a photon of frequency f, that is exactly what is written here. This mass change is the Planck constant times the frequency of that photon divided by the speed of light squared. This balance over here, this beautiful high-tech object, is also called a Kibble balance, and this piece of equipment allows you to compare the force generated by an electrical current with the force of gravity on a certain mass, and by doing so one is basically comparing the mass of an object with the Planck constant, with the standard that is given by the Planck constant. This is a very sophisticated piece of equipment, but keep in mind that in principle now everybody has access to the definition of the kilogram. One does not have to travel to Sèvres anymore or to a national copy and compare your mass with that, since the mass is now defined in terms of a natural constant. A natural constant doesn't belong to a country or doesn't belong to anybody. This is another, let's say, important element in the new system, in the new definition of the kilogram. And in the new system also the Avogadro constant had to be measured accurately, the Avogadro number. And this was done in the Avogadro project, and for that spheres were fabricated, beautiful monocrystalline spheres of silicon-28. And we have an example of such a sphere over here. Look how beautiful this object is. This is a sphere made of pure silicon, monocrystalline silicon in a perfectly spherical shape. Why was this useful? Well, if one now knows the size of this sphere accurately, and one knows the lattice constant of silicon-28, in principle it is possible to count the number of atoms in this sphere. And at the same time, it is possible to weigh this sphere, to take its weight, and then know its mass. So by doing this, the Avogadro number could be determined in a very accurate way. This is the piece of equipment that looks simple, but it is actually quite sophisticated, which was used by the group of Giovanni Mana and Enrico Massa at our institute in Turin to measure this lattice constant of silicon-28. And you might think that this is an easy measurement, but it is actually quite an effort. And there's a lot of things, technological aspects that have to be taken into account, and all these contributions that require a correction and that contribute to the uncertainty of the final result. And these all have to be taken into account and tried to be optimized to get this incredibly accurate number of the lattice constant of silicon-28. And look at the amazing accuracy that you have in this number. Now, I asked Giovanni Mana because I wondered how much time it takes to do such a project, to take such a measurement. A year, maybe 2 years. In the end, it's just a number that you're trying to measure, right? Well, to get this done properly, this was the time schedule that Giovanni showed me. So in 1975, the research started, and it took all the way to 2015 with painstaking improvements to get to a number with this incredible accuracy. So that's 40 years of work to get one number. But one very important number measured in a very accurate way and in such a way that people could really trust this result. The work done by this Avogadro project not only gave the Avogadro number, but it indirectly gave also a very important contribution to the determination of the value of the Planck constant. And what you see here is the different measurements of this Planck constant done by different collaborations and different technologies. And the amazing thing is that all this data then is consistent with each other, done by different people in different parts of the world, but using totally different technologies. And this is then all consistent and ends up in the end in providing you with the best possible value of the Planck constant that you can have. Now, the Planck constant was not the only natural constant that had to be measured. Another measurement that was very important in the new system was the Boltzmann constant, and that together with the Avogadro number was used to redefine the Kelvin. So there you have it. In the end, job done. We have a new system, and this new system is working very well. It is now being implemented in these years, and it is all based on the natural constants. And here you have these values. This is a page with only 7 numbers, but these numbers, to get them right with all these digits, that took decades and decades of work of many scientists all around the world. And I think it is really beautiful to see all those numbers together and to realize how much effort went into this to get this properly done. Notice also that now in the new system, these values do not have an uncertainty anymore. So in the new system, after having measured these values, the new definition now defines them once and for all without uncertainty. So if I work within the system of the SI, these values do not have an error on them anymore. These are now fixed numbers. And it was so many decades of work to make sure that the right numbers were written here. I wanted to show you this photograph because this was an emotional moment. We were all together, governments from all around the world, and all these representatives were there, and everybody had to vote. This was the vote by our Italian representative, and as I said, all these people from all these countries together, and unanimously everybody, one after the other, stood up and voted yes for the new system. And this now allows us to look forward. What is going to happen now that we have a new system that is working perfectly, and we have a lot of technology available to do very accurate measurements with? What are the things that we now have to measure, and what are the things that we now have to look at as metrology community? In particular such that we can contribute to the important questions of our society and of our planet. First of all, we think that it is good to look and to help in activities regarding monitoring of the environment and supporting the development of clean technologies. There will be a lot of data, there is a lot of data from satellites, from terrestrial sensors, from the sea, from the air, and all this data has to be reliable, it has to be taken in a reliable way, and people have to trust this data. This is an important aspect of how the metrology community can contribute here to make sure that people trust these results. And that's important because if political decisions have to be taken, the data on which they are based have to be accurate and have to be trusted. Adding to this is that the environments are often complicated and sometimes really extreme. You can be in places like this, and then it becomes much more difficult to do accurate measurements. So you can be on top of a mountain, you can be in a very cold environment, you can be in a very hot environment, etc. On a very different note, one can think of the environmental impact of a consumer product. If I go to a shop and I buy something, I might want to compare two versions of roughly the same product and take into account how much pollution there is generated by this product. And then there is the manufacturer of this product. It can be that the product is comparable, but in one case it was made in a way that is very much polluting, and in the other case it was made in a way that is not polluting. So it would be good to have this information for the consumer available on the product when it is buying. This is another example of how the metrology community could contribute to this very important topic. Another topic on which we think we should contribute is supporting sustainable energy conversion and clean storage. As you know, Europe has decided that it wants to be climate neutral in 2050. Other continents have made similar arrangements and similar considerations, and that means that a lot of work has to be done to reach this goal, which is an important goal for our future, also on the long term. Clean storage is an important concept in this, and batteries can play an important role. Now think of measuring on a battery can mean things like finding a way to judge if the battery is reliable or not. What will be the lifetime of this battery without having it go through its entire life cycle? That means I have to find the right parameters to measure. Another example is that of a solar cell, a photovoltaic solar cell. Can I find parameters, the right parameters, which give me information on the estimated lifetime of this product? And then we have topics like the energy infrastructure, the distribution of electricity, and for instance also the generation of fuel out of atmospheric CO2, which means that fuel is generated by taking CO2 out of the atmosphere, which is of course a very good thing to do. Then there is the quality of life and health. And examples there include, for instance, biomarkers for biological processes, pathogenic processes, and therapeutical response. But also the quality assessment of food and the food packaging and medicines. Can I, for instance, identify something in the food that I buy in a shop such that I'm sure that this food was actually produced where it is claimed it was, and for instance that it has the quality standard, it respects the quality standards that are declared by the person who is selling it. These kind of measurements are very precious, of course. Then there's other topics like the effect of electromagnetic fields on the human body, ultrasound. An example of this is a group of us recently started to look at the use of ultrasound to help patients that have been infected with the coronavirus and that have these lesions in their lungs, and how ultrasound can be helped, can help them to cure this. Electromagnetic fields, of course, are things like the mobile phone, the electromagnetic fields emitted by the mobile phones. How much are they actually damaging your brain tissue? Things like this. Then there is the digital transformation that is going on of our industry and actually of our society in general. There's going to be an increasing amount of sensors and sensor data, and that will mean that there will be networks of sensors, and all this information has to be processed and has to be certified, and people will have to be able to trust all this information. That's also because decisions will be taken. As I said, for instance, if you have a manufacturing site with a lot of sensors, and this sensor data is now processed by some form of artificial intelligence that tells you, hey, call a technician because next week something will break down probably, then you want to make sure that you can trust this decision and that you can trust this data. But this is now all in a virtual world. So this is the decision being taken somewhere in a virtual world, and the data is being generated, of course, by sensors and processed by neural networks and computers, etc. So it is really important that as a community of scientists that work on measuring things, that we pose ourselves the question, how will measuring things look like in this world which is not so far in the future? It's actually very rapidly developing. Then there is space and applications and research in this context. We have the Copernicus Earth and Environment Observation Program, which is generating a lot of useful data, and many important things can be done with this data. Also, for instance, related to pollution and to the environment. Then there is the Galileo satellite navigation system, which I talked to you about in the beginning of my talk as an example of how a time signal is useful in the context of space and satellites. And then there are topics like quantum key distribution, which will be increasingly relevant for our society. And then last but not least, improving the quality and impact of fundamental scientific research, or also applied scientific research for that matter. So creating synergies between the world of metrology, the science of measurement on one side, and other scientific communities will be of incredible value. So I believe very much in the synergy that can be constructed between the world of metrology on one side and scientific research, fundamental or applied, on the other side. Now, I've tried to give you a flavor of what it took to get to where we are now, and that is we have a beautiful new definition of the units of measure based on the natural constants, which I think is a very elegant concept. There might be some improvements still in the near future, for instance in the definition of the second, and we will dedicate time to implement this system properly. But on top of that, I also wanted to share with you some thoughts on how this technology, which is very powerful, can be used to address important issues for our society and for our planet in general.